Okay, so now, ladies and gentlemen, we're doing some of the most defining things of this exercise. So, what I would like to do now is to go to workplace. We're going to add pathogen reservoirs in workplace and in home. Okay? Now, ladies and gentlemen, pathogen reservoirs have an evolution that's shaped by many things, but often they'll grow over the span of hours depending on heat and humidity conditions or what have you, depending on the type of workplace. Maybe it's a long-term care facility in the Bath area, and you might have MRSA growing there, or it might be a chicken incubator facility, and there might be pathogen growing there, or what have you. And we want to capture the dynamics of that growth, potentially as well as cleaning for that facility. And pathogen die off after some time. And we might be interested to even take into account how humidity and temperature regulation might affect things. So, ladies and gentlemen, what's the level of pathogen contamination? Suppose we want to treat it as a continuous quantity that rises and falls in a gradual way over a continuous time. What sort of construct within the available ones in any logic might be appropriate for representing a continuous quantity that kind of changes over time, sometimes in a regulatory fashion? System dynamics, stocks and flows. Okay? Now there's some trade-offs here we'll talk about later, but it'll be a very exquisitely expressive way for characterizing these stocks and flows, or the pathogen levels. So, ladies and gentlemen, I would like to repair ourselves to the system dynamics palette, and I'd like you to open up the workplace here. And I'd like to drag in to the workplace a stock, ladies and gentlemen. This is going to reflect the reservoir, a pathogen, some amount of pathogen that's there. We'll call it pathogen reservoir that's associated with this workplace. And of course, we could provide many of these. Using the types of tools we use in discrete event modeling, we could indeed make the workplace divided into a set of rooms. I don't know if you remember, but yesterday I showed, it was the day before yesterday actually, I showed how with discrete event modeling, you can actually draw out with the markup palette rooms in a facility and so on. So and treat them as resources. We could actually have rooms in a facility, each having their own pathogen reservoirs. And in fact, we do have models like that for MRSA. One built by a talented student, Narjas Shajati, where basically we have reservoirs in each room and even on things like door handles or bath areas or what have you, associated with the facility. Here, I'm just going to go a little bit simpler in the interest of time and so on. We're going to have one pathogen reservoir, ladies and gentlemen, for the whole facility. Okay? Okay. So, ladies and gentlemen, we're going to now have two flows, one into the pathogen reservoir and one out of the pathogen reservoir, okay? So I'd like to have a inflow to the pathogen reservoir here called shed pathogen, okay? And an outflow called pathogen inactivation. And this pathogen inactivation is going to capture sort of the dynamics of the endogenous growth of pathogen as well as its die-off. And the idea is going to be if you don't have shedding going on, it's going to tend to die off over time. But if you do have shedding going on, it will tend to build up, and it will die off at a certain rate. And later we could put in cleaning regimens and so on if we wanted to that would affect this regimen, this pathogen reservoir. But ladies and gentlemen, we're going to put in place a very simple mechanism, a mechanism that we had yesterday for that weight dynamic state chart, which is going to be associated with what's called a first order delay. And this is a common regulatory construct. It represents the fact that if there's no pathogen reservoir, nothing in the pathogen reservoir, we'll have zero flow out, zero inactivation. But with more pathogen reservoir, the more pathogen inactivation per unit time will tend to be taking place. If we have a huge pathogen reservoir, we'll have more die-off going on in terms of, on a per time unit basis, bacteria dying than if we have very, very little. So this outflow, in short, needs to depend on the value of the stock. It's not a constant outflow. In other words, there's inactivation which takes place at a fixed time constant, okay? And this time constant will be called mean workplace pathogen lifetime, okay? What sort of parameter do you think that will be? Can anyone say? It'll be a mean lifetime. What does that sound like? A time. Okay? Okay. Ladies and gentlemen, that's good. Okay. And I think we will assume for this, and unfortunately I don't have a good note here on what this is when I've done this in the past. Okay, yeah, I should probably double check this. I'll make it. I'll declare here that it will be maybe 10 days, something on that order. Okay, now maybe what that will mean is if you don't shed, how quickly does the pathogen decline on an exponential level? This could be related to I think it's going to be related to the natural log of the same as the natural log of the half-life of it in the absence of shedding. How long will it take the pathogen reservoir to reach half its level? This would be the natural log of that if we want to express it in those terms. I'll try to come back and pin down a better value for that in a bit. Okay, so mean workplace pathogen lifetime. That's one of the things depended on by this flow. So we draw a link to that flow to reflect the fact that the flow depends on this parameter. Okay. Next, ladies and gentlemen, it must also, I argued, depend on this. If there's no pathogen reservoir, if it's zero, there's going to be no inactivation going on. If the pathogen reservoir is very large, there'll be large amounts of inactivation going on. So this flow, in short, has to depend on both. Now, there are quite some literatures on dynamics of pathogens. I've done quite a bit of immunological modeling, for example, and even in environmental context, we could probably characterize this dynamics in a fairly articulated way, reflecting humidity and temperature levels and the amount of particulate matter perhaps that settles or what have you to form the surface area in which pathogen can grow. That can be captured quite readily in this process by not having just a fixed parameter, but having something that depends on several parameters in environmental conditions. We're not going to do that right now, but I'd be glad to describe how that will be done. And one of the ways is you put it a dynamic variable, and that would be the value of that of that variable be set by other environmental conditions. For now, we're just for pathogen inactivation, we're going to put a simple formula, which will be pathogen reservoir, and this is a theory-based formula based on theory of system dynamics and how in the mathematics involved. It's pathogen reservoir divided by the mean pathogen lifetime. That's associated with what's called a first order delay. And that will mean that a given unit of pathogen will tend to reside here with an exponentially distributed residence time with this mean. That's implied by this formula, the mathematics behind it. Okay? Ladies and gentlemen, so my point is, one of the things recommending stock and flow depictions is there's often theory in the literature about how to model things with ODEs, with ordinary differential equations or stocks and flows or compartmental models that you can just apply to bring in a theory-based model into your simulation. And that's a real asset compared to writing your own custom rules where you don't have theory to guide it. So stocks and flows, in addition to being crisp and expressive in their description of the dynamics of quantities, often have a lot of theory behind them, particularly for regulatory processes. Here, our representation is very decidedly stylized and simplistic, but I'm confident that if I were to spend a week researching the literature on pathogen dynamics, there's probably all sorts of ways this could be elaborated still within the stock and flow framework. Okay, so so we have this first order delay here, and this theory why it's called the first order delay, and you can find me giving talks about it to my students separately. So we filled in that components. You notice system dynamics is declarative. We basically say what relation we want to hold here, and it will take care of calculating this. There's no code writing here in a sophisticated way. Instead, we state the mathematical relationships that obtain between different things in this model. Okay, but ladies and gentlemen, we're going to set our sights on this inflow as well. Before doing that, I'd like to make sure the pathogen reservoir initially stays starts at 0. Okay? 0. Okay. Now, here we go. Here we go. Okay. So, what I'd like to do is to do the following. Right. Okay. I'd like to go to main. We want to set this formula for shed pathogen. But to do that, we're going to have to put in place a wee bit of supporting machinery. We need to, well, let me ask you, this shed pathogen, the way we're representing it here right now, that's going to depend on the number of people who are shedding at that location. So they're going to be shedding MRSA or Clostridium difficile or maybe an animal shedding E. coli or what have you. And so the amount of shed is going to depend on how many animals are there, people are there, and the health state potentially of that animal. So if we're thinking about cholera, it will depend on the amount of shedding that goes on with Vibrio cholerae at that location. So we're going to need to put in place a mechanism to compute how much shed pathogen is there, how many people are ill at that location. So what I'd like to do, ladies and gentlemen, is do the following, okay? I would like to go and go to main, okay? In main, because we're going to use this from two different places. In main, I would like to go and create a create a function called count infective in group. Okay? So in main, we're going to go to agent and drag a function. And this function will be called count infective. In fact, probably should be called count infectives or count shedders in group. That's better. Oh man. Shedders in group. After all, we call them shedders in that diagram. Okay? Okay, ladies and gentlemen. Great. Okay. And what this is going to take in as a formula is it's going to take, so this is going to return a value, which is going to be what? If it returns a count, what do you think it will be? It'll be an integer indeed. An integer, ladies and gentlemen. It's going to return an integer, and it's going to need some information to do its job. To count the number of shedders in a certain group, what do you think it's going to need to do its job? It's going to need to be told which what? Let me say that again. To count the number of shedders in a group, it needs to be told over which what to count. Over which group? To tell it which group. To do its job, so give me a group, but I'll tell you the number of shedders in that group of people. Does that make sense? Okay. So, we have a parameter here that will be called group. And its type will be list of person. You notice now this is going to be unfamiliar territory. What this is saying is it's a list of people. It's a person 1, person 2, person 3, kind of a list. And this thing here and this thing here are just delimiters to say it's a list of person. That's just how we write it. It could have been, parentheses in some other language, but this is how you write it in Java. A list of person. Yeah. Yeah.
Yeah, I don't have that option on my drop down.
You're gonna type it.
You have to, okay. You have to, you can type it out. Yeah, if you do a drop down, it's not one of the options. You have to type, I'll do it, list person. So those things are not greater than and less than signs. They're just serving like this would be. In other languages, it would look like this, or parentheses, but it's just here it's being used like that. It's an unfortunate thing. This is one of the times where I feel Java is not a very helpful language. Are we okay with that? Some list of people I'm going to give this. Okay? Okay, ladies and gentlemen. Now, having gotten that list, this is what I would like to do. For person, I'm going to call each person that group person. Okay, sorry, I need to do one thing before this. Int running count of shedders equals 0. What is this thing? You've seen it before. It's the short name for this value I'm going to be accumulating. Running, well, you might disagree that it's short, but it's a name to call a value. And I'm going to be changing this value. This is what's called a local variable. It's just a variable I'm using here out of convenience, just for the sake of this code, and I'm giving it a nice name, for each person in this group, what do you think I need to do? To count the number of shedders, what do you think I need to do? Does anyone want to say? How would you count the shedders? If you had a pad, you know, a notepad, so a clipboard, and you had a group of people in front of you, and you could go through and ask them, are you shedding, are you shedding, are you shedding, and they'd be guaranteed to tell you the answer. What would you do for each of them? Well, you'd first ask, are you shedding? And if they're shedding, you'd tick one off your clipboard. Record one more. In other words, you'd say, okay, we have one more yet, and that's all this is going to do. So we have to ask, is this person shedding? If person, okay, dot in state, and what state do we ask about?
Shedding.
Yeah. Now, I wish we could just say shedding, but we really need to say person dot shedding. I believe. I don't think it's just going to allow us to say shedding by itself, because it will say, well, which one? No, it's unhappy with that. You need person dot shedding. Shedding with respect to person. Do you remember where we've seen that before? Within the past hour?
In the statistics.
In the statistics. We did the same basic thing. If this is the case, then what do we need to do? If they're a shedder, what do we need to do with this running count? We need to make it one bigger, right? This equals this plus that, like that. But we could do it more briefly by just saying this. We'll just make it one larger, and then, so that's our running count. We run through each person in the group. We make it one larger if they're ill, if they're shedding, and then what do we return as the count across the entire group? What do we return back? We return back that running count. So suppose we have 100 people. You. We're going down and recording the number that are shedding. Bum, bum, bum. You're shedding, no. Okay. You're shedding, no. You shedding, yeah. You shedding, no. You shedding, no. You shedding, yep. I record that. So I've got a count being accumulated, and then I return the count. That's what the function's job in life is. Given a group, it will return for you a count of shedders in that group. That's what the function does for its job. That's its purpose in life, is to return the number of shedders which lie in this group. Are we okay with that? Can you convince yourself this is what this does? It starts with 0. If there ain't nobody in that group, we're going to return 0. If there's one person in the group and they are a shedder, we'll make this 1 then, and then we'll return it. If there's 2 people in the group and one's a shedder, one's not, let's say the first is not a shedder, we'll go through, okay, the first person, are they a shedder? Nope. It'll continue on to the next one, or okay, this next person, are they a shedder? Yep. We'll increment it, it becomes 1, and then, ladies and gentlemen, we return 1. What's the number of shedders in that group? Suppose both were shedders. We come down here, start at 0. Okay, going through first person, are they a shedder? Yeah. Increment this, goes from 0 to 1. Next person, are you a shedder? Yeah. Increment it from 1 to 2. Return 2. Does that make sense? Okay. 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 If anyone wants further explanation on that, Kurt would also probably have his own way of explaining things and so on, and that's also good. Okay? Are we okay with that? Count shedders in group. Okay. Ladies and gentlemen, we're largely, that was the key bit of logic. And as always, I apologize when showing you the effrontery of such logic, such a bit of code. Okay. Okay. Oh, we should probably, yeah, we should probably mumble. Okay, this next thing. Fine. I'll just leave it like that. Okay. Okay, ladies and gentlemen. So what I'd like to do is to do the following. Okay. What I'd like to do is to go to workplace. We're going back to workplace, and we're going to use this function. Who's going to benefit from it? For whose purpose have we set that function into action? For our own, ladies and gentlemen. You will now enjoy the sweet fruits of your work. Okay? Are we okay with this? Okay. Okay, so ladies and gentlemen. So what we need to do here for shed pathogen is we're going to put in a formula for shed pathogen, okay? And oh yeah, we need one other. I'm sorry, we need one other thing in main, and that is there's got to be a parameter in main that is called per capita shedding rate, okay? Per capita shedding rate. Okay. So we need to go to main and add a parameter. Hey, come on. Parameter per capita shedding rate. Okay. And you're going to have to excuse me because this is the second parameter where I don't have a good note on its value, so I'm just going to go and open up a previous model we built with this and get exactly that. Okay, so this is environmental contamination hybrid. Here we go. Here we go. Okay, and I am going to open up main, and let's go look. Mean pathogen lifetime. Okay, mean pathogen lifetime was set to 3 days there, and then we need to look at sorry, workplace. I think there was per capita shedding rate was 1.0. Okay, great. Okay, so now I can close this. Okay, so ladies and gentlemen, per capita shedding rate that we want is going to be 1.0. It's in main. Should be a rate. Thank you. A rate per hour. Right. Okay. Great. And probably we should move these things over just so they're not occluding that area. Okay.
Is there a reason I wouldn't have per hour in my drop down?
Oh. Okay. Kurt, do you want to check that out? Per capita shedding rate? Should have per hour, I would think. Right. Yeah. Okay. Okay, so ladies and gentlemen, per capita shedding rate is 1.0 per hour. Okay. So for the workplace, ladies and gentlemen, for the formula for shed pathogen, we're going to do the following. We're going to have the following formula. Main dot per capita shedding rate, per capita, oh, I'm putting this in the description. What am I doing? For the shed pathogen formula, this should be main dot per capita, main dot per capita shedding rate. Okay? Per capita shedding rate times, so per capita shedding rate times count infective in group, main dot count infective in group. Count shedders in group. Who wrote that? Count shedders in group. Remember who wrote that?
That's me.
You did. You just did, about 5 minutes ago. Remember that? Count shedders in group. Do you remember that? Okay, how could you forget? Okay, remember that was the one where we counted up? Went through each person? Okay. Count, what's that?
Very memorable.
Yeah. Yeah, maybe the memory gets blotted out sometimes. Okay, now, ladies and gentlemen. Okay, I'd like to do this. So inside count shedders group, which is the group? This dot get, so agents in range yeah, okay. Agents in range. Okay. And in range of what? Well, we're going to ask main dot population in what range? We're going to ask within 10 units. Okay. So let me make sure this is hunky-dory. And yes, it's hunky-dory. So let me put it up on the big screen. Okay, there we go. And I'm going to split this into 2 lines just so you could kind of see this written out fully. Okay, so Maine has a per capita shedding rate. We're going to multiply that. That's per capita. So to find out the shedding across all shedders, we're going to multiply it by the number of people around us who are shedding. And this dot agents in range is going to find the agents in the main population who lie within 10 units of ourselves. Okay? This is within 10 units of ourselves here. Okay, this is what this is. Okay, and this is going to count the shedders in the group, in that group who, of those agents who lie within 10 units of ourselves. How many shedders are there? We're going to multiply it by the per capita shedding rate, and that's going to give us the inflow, ladies and gentlemen, of shed pathogen. Does that make sense? That's the flow in. How much pathogen is coming in per unit time? Well, there's a per capita shedding rate per unit time times the number of shedders. This is a per capita rate, so we multiply it times the number of heads, the number of people who are shedding. Are we okay? So this is per shedding capita, yeah. Are we okay with that? Do you want me to put this up here a bit longer? This 10 is a distance, and we should probably turn it into a parameter, but right now it's a distance. Can I run this? What do you think? Let's run this, okay? Okay, so here we go, and ladies and gentlemen, here we go, and we're going to have here this workplace and the home, and let's go down to the level of workplace, okay? And here we have in the workplace some pathogen in the pathogen reservoir, and now we have it building up. Why is that, do you think? Why would it be building up? So this pathogen reservoir is rising, and now it's declining. And I suspect in another 16 hours or so, it will start to rise again. Why do you think it's rising?
We have the room at 11:30.
Oh, you do?
Yeah.
Okay. You're going to speak with this gentleman, and he
Okay.
can confer with you.
Okay, this
Okay.
is so cool. Is that a micro?
It is.
Oh, I love it.
Yeah. Great.
Excuse me.
Yeah. So, ladies and gentlemen, you have this building up, declining, building up, declining. Why is this building up? What must be there? Why is this pathogen reservoir increasing for some time and then decreasing? Anyone? What causes the reservoir to increase?
Increase in shedding rate?
It's in shedding. So there's people here shedding during part of the day, and then they go home and sleep, and then they shed more. And so these individuals here, right, some of them are coming in infected, evidently, to a factory, and are shedding pathogen during that time. At first, it doesn't look like there was any pathogen being shed. Okay, now there's, okay, there was for a bit, it looks like, two. Okay, this is interesting, yeah. So much of the time it's 0. Why is that? Now look, 3. Because there's 3 people shedding during the day right now. 4, okay? So we're getting a growth in the amount of pathogen to which they're exposed. So this is the dynamics of pathogen within a given facility, right? Now there's six people here who are ill. So we have dynamics of pathogen, build up, decay, build up, decay. But ladies and gentlemen, what's one critical thing that's missing? Well, right now, we don't have people getting sick from that pathogen, do we?
You get to relocate to the floor so that we're not illness.
Okay. Okay. Okay, so I will pack up here. Okay.
Let's
So,
take CPR for him.
right. We'll come back and we'll finish up the infection of people from environmental pathogen.